In this video, I will show you how a microscopic turbine inside your cells spins at a staggering 6,000 RPM to power your life. We'll explore the architecture of ATP synthase, how a proton force fuels the C-ring motor, and why different species use different gears to survive. Finally, you'll see the exact molecular squeeze that converts raw energy into ATP. ATP synthase is an engineering marvel composed of four key parts: the C-ring turbine, the rotating shaft, the ATP producing unit, and the support stalk. The C-ring turbine sits directly within the membrane. It forms a circular rotor made of repeating protein subunits. As protons flow through the motor, they bind to the ring, driving its stepwise rotation. The rotating shaft, called the gamma subunit, is attached at the center of the ring. As the C-ring turns, this shaft spins with it, acting as a molecular drive shaft. It transmits rotational energy downward into the core of the enzyme. The ATP producing unit, known as the F1 head, sits below the membrane. Here, rotation is converted into chemistry. As the shaft turns, it forces catalytic subunits to change shape, driving ATP formation. The support stalk, or stator, provides structural stability. It holds the ATP-producing unit firmly in place. This rigid anchor prevents the complex from rotating as a whole, allowing energy to be captured. To understand why the C-ring rotates, we must first understand the proton motive force, or PMF. Across the membrane, protons are unevenly distributed. One side holds many, while the other has fewer. Positively charged protons can move freely in water, but the membrane is an oily, hydrophobic barrier they cannot cross. Like water behind a dam, protons accumulate, creating stored energy known as the PMF. ATP synthase provides the gate they can pass through. This is the energy source that drives its rotation. An arginine residue in the ion pump is used for proton capture. Meanwhile, each subunit of the C-ring contains a negatively charged residue, typically aspartate. In the oily environment of the membrane, these charges are unfavorable. But when a proton is transferred from the arginine to the aspartate, it neutralizes the charge. This neutralization allows that C subunit to move freely into the membrane. As it moves, it physically pushes the entire ring forward. Each proton is carried nearly a full circle until it reaches an exit channel, where it is released to the other side of the membrane. In an 8-subunit C-ring, one full rotation requires only 8 protons. Because 3 ATP molecules are produced per rotation, this results in an efficiency of roughly 2.7 protons per ATP, among the most efficient ATP synthases known. ATP synthase can use different C-ring sizes in different species. From 8 subunits in mammals to more than 17 in some bacteria, the number of subunits determines how many protons are required per rotation. This works like a car's gear system. Smaller C-rings act like high gear, producing ATP efficiently when proton flow is strong. Larger C-rings act like low gear, maintaining reliable rotation under weaker or fluctuating proton gradients. ATP is a small molecule containing 3 phosphate groups linked together in a chain. Each phosphate carries a negative charge. These charges strongly repel one another, so as long as the phosphates remain linked, energy is stored in this strained configuration. When ATP is used, the terminal phosphate is released. This relieves electrostatic repulsion and releases energy that powers cellular work. ATP synthase catalyzes the reverse process. It uses conformational changes of the F1 head subunits to force the final phosphate back into place, rebuilding this high-energy molecule. In essence, ATP synthase converts motion into chemical tension, storing energy in the bonds of ATP until the cell needs it. Inside the F1 head are 3 catalytic subunits arranged in a ring. Although they are chemically identical, they never behave the same way at the same time. As the central shaft rotates, it forces each subunit into a different shape, creating three distinct states: the open state, the loose state, and the tight state. In the tight state, mechanical force from shaft rotation squeezes ADP and phosphate together, forming ATP. With every 120-degree turn of the shaft, the subunits cycle through the three states. After one full rotation, all three sites have completed the cycle, producing 3 ATP molecules. This is the molecular squeeze, where rotation becomes chemistry and motion becomes life's energy. ATP synthase is a chemomechanical energy converter. Operating with high efficiency and strict structural coordination, ATP synthase provides the primary source of ATP for nearly all cellular processes, making it one of the most fundamental energy-producing systems in biology.